from our usual lecture time, but I hope that we can cope with that and then finish it. So, okay, I haven't given to you guys. See, I forgot to. I think I have forgotten this accreditation thing is so much work. So let me just. I have put it on Canvas, but I forgot to make it available for the second week. I will do it. I will do it. Don't worry, I will do it right now. Thank you, whoever messaged me. I will make it available for you guys. Don't worry. So for today, our lecture is on stoichiometry, and stoichiometry is nothing. It's a hard word, but is in a simple way to put that stoichiometry is hold on. Yeah, now it is open. I have just made it available, so hope that you can see it now. All right, so stoichiometry. And stoichiometry is about balancing the reaction. All right, if you can balance the equation, then that means your stoichiometry that you're making, the stoichiometry things, I mean, you're balancing the equation. And now how do I turn off from my phone? Teams is making problem. So today we'll be looking at the stoichiometry. And first of all, I mean, why do we need stoichiometry? It is one single most important thing to know the amount or quantity of our reaction or reactant or product or any other matter related to the reaction. It is the single most important thing that we need to know. All right, because we want to produce a certain amount of product, or we have certain amount of product in our hand, and we want to, before we go for the production, we have to do the production. Means you have to invest some time, some resources, some money, some your workforce. But before, if we know that how much you are going to produce the product from this matter you have in your hand, we can find out already how much product you will produce, and then we'll proceed whether it's profitable for us or not. That is a different thing. So that is why stoichiometry is very important. And our learning, our objective today is to balance the equation. How do we balance? There is some, I mean, we will be going there. And then the quantity of a reaction or product. And how do you find out the quantity of a reaction or product using the stoichiometry, first of all, and when and how should we be using limiting reactant? What is the limiting reactant and why do we need the limiting reactant? And later on, the composition, how do we determine the composition or purity of a material used by gravimetric analysis. Gravimetric analysis is also another term. I don't know whether you are familiar with, but this means that to measure and do the analysis depends on the weight of the material. That is called the gravimetric analysis. Okay, so balanced equation, writing the balanced equation. And before I proceed there, I think I'll turn off the camera because probably it is taking up the bandwidth for you guys, and it will be smooth in that way. Okay, so balancing the equation. There are two types of reaction. One chemical reaction 1 and then chemical reaction 2. One is the oxidation reduction reaction, and then there will be a, we'll go to the chemical reaction 2 type 2, that will be a double displacement reaction. So Oxidation and a reduction reaction. We all, I'm sure that you have been exposed to this idea of oxidation and a reduction, right? When there is a transfer of electron among the reactant, all right? Like I am having A and B. I am having A and B as a reactant. This A and B is, for example, and it can be many things, or it can be many other things, not everything, but many things. And when A and B, let's say this is one chemical, certain type of chemical, B is another certain type of chemical. When they are in a reaction mixture, not all the reaction mixture, there are some condition that the reaction can happen or will happen. So when there is a reaction mixture, there will be electron transfer between them, right? There will be electron transfer between them. So probably the electron A from A will move towards chemical B or vice versa in that way. So depends on the electron transfer. We know which is oxidation and reduction. So we'll go more about it later. Oxidation reduction, because we need to know the oxidation state, and only then we'll determine which one is having oxidation, which one is having reduction. But for your information, I am sure that you already know about it. Oxidation is losing and reduction is gaining. Okay, so oil rig, we know that it is the oil rig. Oxidation of losing of electron, losing of what? Of course, the electron. We are talking about the electron, losing of electron, and reduction is gaining of electron. Gaining of what? Gaining of electron. So oil rig, I think it is a quite good mnemonic for you to remember in this way, because oil rig, you know that in the sea, or sometimes you can see in the Shell or Petronas in Bintulu or Miri, they have inside the sea the oil. They extract the oil from in the sea underneath the surface. So they produce something like that in the sea, and it has legs. It is in the water. This leg should be like this. So it is in the water, and then a pipe goes beneath the surface of the seabed, and then the oil comes out. So this is called the oil rig. So this way we can remember. This way we can remember the oxidation and reduction. So okay, oil rig is oxidation and reduction. Oxidation is losing of electron. Reduction is gaining of electron. Now, this oxidation and reduction reaction, it has been distributed or divided into three different segments, three different sections. One is combination, another one is decomposition, and single displacement. All right. So combination is quite intuitive thing, and you understand combination means both of them are combining together. That means they're just getting attached to each other. So this is a combination. Decomposition means it is breaking apart. Initially it was there, and we want them to break apart. So this is a decomposition. It is decomposing from original state. So from combination, that AB, if we consider only this case, so AB, and then if we do the decomposition, we get the same product that we started with in combination. All right, mostly, not everything. And then single displacement, when this AB, like two of the compounds are together in this AB are here, two of the elements, and it produces a compound. It can be two elements, it can be many more elements, more than two elements as well. 3, 4, 5 elements can be together, and then we can call it a decomposition, and when they break apart, or same goes for the combination. So when these many compounds together and then we bring something close to it in reaction, some of this, either A or B is moved and then C is coming in, or C is replacing something that we started with. So that will be a single displacement reaction. Okay, that is called the single displacement reaction. So oxidation reduction we can divide into three different ways: combination, decomposition, and single displacement. All right. But the main thing is, when we write the equation, we have to make sure that their mole ratio is, it makes sense, or it is as per they occur in the product, right? We can put here 5 moles. Where is my cursor? Yeah, we can put it here 5, and here is 10. But aluminium oxide or alumina, this is alumina or aluminum oxide, is always Al2O3. You cannot make it Al4 and O5. No, it is not an alumina. All right, alumina is always Al2O3. So how it is happening? If it is Al2O3, how is it happening? That how is happening, or how much aluminium and oxygen we need, that is the balancing of equation. We have to know that there are 2 aluminiums is here atoms, right? The 2 aluminium atom in this molecule, and 3 aluminium atom, oxygen atom in this uh, molecule. So if we add 2 aluminium in front of this alumina and 3 in front, then it makes better sense, right? It makes sense, and it is showing that it is what do you call it, balanced equation. Now decomposition reaction. So when lead nitrate.
Excuse me, sir.
Yeah.
So it's 2 aluminium, and won't that be 6 oxygen over there?
Who is
the
it?
Balancing? A combination A.
Jamud?
Yes, sir.
Are you talking? Yeah. Thank you, Jamud.
Yeah.
I appreciate very much of this. Actually, I put it wrong way so that I want a student to talk.
Sure.
So thank you very much. Yeah.
Right.
So I mean, Jamud, you got it right. Can I get anyone else to what will be the correct one to talk? Is there anyone else want to contribute, or you want to just voice up? What do you think that what should we put to make it perfect or correct? Anybody else want to chip in? I'm here. I appreciate, really. Okay.
I think it will be 2 aluminium plus
Yeah.
3 O2,
Okay.
then 2 aluminium, 2 oxygen 3.
Okay,
Yeah,
so you
yeah.
say I should put 2 here, right?
Here and make the aluminium 4.
Okay, great. Yes, exactly. So you understand. I mean, thank you very much, all of you, and especially Munib and Chamat, that yes, this is how important it is. It like those who are still confused, I probably I can get some analogy or example, like if you want to make a cake, right? If you want to bake a cake, you need, what do you need? You need butter, you need flour, you need what else? Chocolate probably. Only if you put butter or only if you put flour, you will never get a cake. Or if you put 1 kg of butter, 1 kg of flour, probably you will not get a cake. So you have to put it in proportion to make it a cake. And this is the proportion. Like chemistry is like cooking, and the best cook or best chef is who knows, who understand exactly how much and when, how long you will do the reaction. So you this is it, the balancing of the equation. You have to balance the equation by using the correct balance. Is my hold on here. Okay, I turn off the camera again for smooth transition. Okay, so like this, if you have any question, please do ask the question, unmute yourself and ask the question. I appreciate it very much. Decomposition reaction, same thing goes for lead oxide, lead nitrate actually, all right, and it is decomposing into lead oxide. It is probably, you will think that why not, it is just lead and nitrogen or nitrogen oxide. That does not happen in that way, because if we just produce lead and nitrogen dioxide, it will be hard to balance the equation, or in nature it is very hard to be balanced. So either you have to more lead you have to bring in, or more nitrogen you have to bring. But in this way, when we put the lead oxide and nitrogen dioxide, it is much more, in a better way, it is balancing, and actually the decomposition happens in this way. So from two lead nitrate, lead oxide is produced, 4 nitrogen dioxide is produced, and 1 oxygen gas is produced as well. All right. So this is how we should be balancing the equation. So if we look back, just like we discussed that we started with 2 lead. So here there is 2 lead, and another way, when we multiply with 2, we have 2 nitrogen, is it? First of all, we should multiply with this figure, so that I have 4 nitrogen here already. All right. So 2 nitrogen for, multiplying with these 2, and then again multiplying these 2 with these 2. So it's altogether 4 nitrogen. All right. And here oxygen is 3 atoms in it, but overall in this molecule there are 2 nitrate ion. What is ion? Later we are coming there actually. So there are 2 here, suffix. When we add 2, that means there are 6 oxygen atom multiplied by these 2. So there are 12 oxygen atom should be there. So now we have to make sure that on the right side, everything, all the species that we used here in this reaction or started with, follow or balance out exact same figure. If is one short or half short, your reaction is not balanced, right? So what you said, that we have two lead, and we have 4 nitrogen. So this is 4 nitrogen, and it is already balanced. So lead and nitrogen is balanced, and now we have another oxygen to balance, and which has 12 oxygen atoms. So 2 is here, and 4 times 2, 8 is there. 8 oxygen and 2 here. So it's oxygen, yeah. So 2 oxygen, 8 oxygen, plus another 2 from here, because here 2. So another 2. So 8 to 10 plus 2, 12. It is not 80. It looks like 80, 20, but actually it is oxygen. It is oxygen. So 12 oxygen is there already. So now this reaction is totally balanced. There is no simple or steadfast trick for balancing the equation. You have to, most of the time it's trial and error basis, but what you can do is you can stick to one specific species. First balance that species, and then you move to another species to balance. And if this type of combined or complex, then just balance this one first. Don't start with this magnesium or a simple one, so that once this complex is balanced, it is much easier to balance the simple one. All right, so you don't start with, okay, I will do this and do this one. No, you just balance this complex one first, only then move to this simple one. So that is could be another one trick. What I do actually, there is no straightforward rule. So single displacement is a magnesium, and single displacement, it means this magnesium will replace something from this HCl. All right, and what is magnesium doing is magnesium is taking this chloride to itself because it is more powerful. So it is taking more powerful than hydrogen in this sense, chemical reactivity series. So this chlorine is coming to magnesium, is bonded with magnesium and becoming chloride, magnesium chloride, and hydrogen gas. All right, so in this way we can balance the equation. So stoichiometry is the study of relationship of mole ratio between two or more substances undergoing a chemical reaction. In a balanced chemical equation, is particularly useful for calculating the quantity of substances consumed or produced from the product in chemical reactions. So what I said that if you want to know the quantity, and believe it or not, for the cake or for the cookies or for the cooking as well, what I said, your stoichiometry, chemical stoichiometry for chemical reaction is very important. If you understand more chemistry, or you have better understanding or knowledge of chemistry, you can apply this thing to your cooking. Even for making tea, you will see the result is better. All right. So now, as I said, or we said, that it is particularly useful for calculating the quantities of substances consumed in the reactant or product. So one example of this can be this way, that the airbag. Every one of us know or are aware of the usefulness of this airbag. If nowadays any car comes from the industry, from the factory, and it does not have the airbag, I'm sure you are not going to buy this one. I'm not going to buy that one. I'm sure you are not going to buy that either. So everybody knows what is the use of this airbag, and this airbag is actually filled up with this nitrogen gas, but there is a big but in here for this question, for this problem, that this nitrogen amount shouldn't be more than required. Okay, let's say that for this specific airbag, for this specific car, it is 67 liter, but for maybe other cars, for other use, it can be any other volume. All right. If it is more than that, 67, what will happen? It will push the driver towards back too much, so that it will not be helpful anyway, but probably it will be dangerous, more dangerous if it is more than that. Or if it is less than that, if it is not 67, is 27, then it is not going to help or going to protect you from accident either. So that is why this number or volume is very important. But how it is produced, this nitrogen gas? It is an explosive reaction, so that the explosive reaction goes on, and then the airbag become inflated. So the passenger is saved. What happens is, for this production of nitrogen, sodium azide is used. Sodium azide. This is NaN3. So there is sodium and nitrogen. So there are 3 atoms of nitrogen in this molecule, right? There are 3 atoms of nitrogen in this molecule. We can see from the symbol. And it is a solid. S means it is solid. S means it is solid. G means it is gas. Sometimes we do not write G, we just make an upward arrow to show that this is a gas, it is going up, right? This is also acceptable. Okay, so this is solid, sodium azide is solid, nitrogen sodium. It is asking us calculate the mass of sodium azide needed to produce enough gas at 300 degrees centigrade and 101 kilopascal. All right. For gas, the temperature and pressure is very, very important, right? Otherwise, we will never know how much is actually the gas is. So can anybody tell me whether we can find the sodium azide, mass of sodium azide from this reaction? Looking at this reaction, can we find? Do you think that it is we can find? Or is there anything missing? Yeah, but he says that we can find. Yes, half true actually. No, we cannot exactly find because this reaction is not balanced. You see, there is one sodium here. There is one sodium there. Oh, that's good. But there is 3 atoms of nitrogen and then it is only 2 atoms of nitrogen here. So how? Where is the another nitrogen goes? It cannot just be vanished, right? It has to be here. It will come here. How does it come here? In this way. This is how we balance the equation. So 2 moles, all right? We say 2 moles of sodium azide is reacting with 2 moles of sodium and producing 3 moles of nitrogen. And now from today I start this. I will be talking about this number of moles, molarity, atoms, especially the number of moles, right? And I will be continuing throughout the semester. I do not care if you are bored or if you said that, oh, it's too much you are talking. I will still continue to talk about this because this is very important. So 2 moles of sodium azide will be required for this type of reaction to produce 3 moles of nitrogen gas. All right. So 3 moles of nitrogen gas will be produced from 2 moles of sodium azide. This is important. First, we have to establish the stoichiometry, that means the balancing of the equation. Now it is balanced. So 3 times 2 is 6 nitrogen and 3 times 2 is 6 nitrogen on the either side, or a reactant and product side. So on the right side, on the right of the arrow, right side of the arrow, this is the right hand side. I don't know whether you are seeing what I'm saying. On the left side, it is left. So left side is product. It's the product side actually, and it is a sorry, reactant side. It is reactant side, and on the right side is the product side. Right of what? Right of the arrow. Side of the arrow is the product. The left side of the arrow is reactant. The ratio, see that ratio of number of moles of product side and reactant side is same. So now we can proceed. We are good to go now. The solution for this problem is 2 moles of sodium azide is producing 3 moles of nitrogen. For this case, we are not considering this because this is not our interest. Our interest is how to find out how, 67 liter of nitrogen gas from how many gram of sodium azide. How many gram of sodium azide do I need to use so that I can get 67 liter of sodium and nitrogen gas? when I'm saying, just for information, when I'm saying that sodium is not our concern, not our concern for this here, only for our calculation for this purpose. Is also our concern. I mean, if it is in real life engineering, we have to consider the sodium as well. Probably we'll talk later on. So this sodium azide, now, I mean, what is the ratio of this stoichiometric coefficient? This is a number of moles. This is also the number of moles, but this is also called the stoichiometric coefficient. Okay, stoichiometric coefficient. This is stoichiometric coefficient. So 2:3. That means if I add or use 2 moles of sodium azide, I will produce 3 moles of nitrogen. All right, I can produce from 2 moles, I can produce 3 moles of nitrogen. So the sodium azide, we need to know it is, the ratio is 2:3, and this is our unknown substance, or this is what we want to know, right? This is what we want to know according to the problem that is given. This is what we want to know. So this is why we put it on the numerator, and this is in the bottom. All right, so this is how we will put this reaction together. And if we want to see it step by step, that the question is asking us 67 liter of sodium nitrogen gas at 300 degrees centigrade and 101 kilopascal. From here, from looking at here, 67 liter of nitrogen gas, sorry, 67 liter of nitrogen gas. So how can I convert it back to this so that I can use this ratio? We have to produce or convert this 67 liter to number of moles, right? Number of moles. How can I convert this 67 liters to number of moles? That is important. And for this, we are fortunate that we already have the gas law. PV equals nRT, right? PV equals nRT. So from there, PV equals nRT, we will find the number of moles in 67 liter. And since the temperature and pressure is given as well, so it should not be any problem. Hopefully it will not be a problem. And once we find the number of moles of nitrogen, 67 liter of nitrogen, that means we can relate it nicely and easily. So 3:2, so how many moles is to how many sodium azide as well. All right, so number of moles, PV equals nRT. 101 kilopascal, so P is 101 kilopascal, is given here. V is the volume, that is 67 liter, and temperature is T, that is 300 Kelvin, and 300 degrees centigrade. So 300 degrees centigrade means how many Kelvin? Remember that in chemistry or chemical calculation, we always use Kelvin, not degree centigrade, right? So one thing should to be cautious of. All right, so another thing is R, value of R. There are two different values, not two. There are many values of R, but sometimes students do not understand the unit. They do not take consideration of the unit. They just use 8.31. It does not, the R is not always 8.31. It depends on what unit you are using. Usually for chemistry, we use 8.31 or 0.820. Okay. So these two type of value use, but depends on what type of unit you are using. Here it is kilopascal. Here it is kilopascal, liter, and Kelvin. And that is why it is 8.31. If it is an atmosphere, liter, and Kelvin, then it will be 0.0821. All right, so don't be confused with that and be careful. Don't use the wrong value. If you use the wrong value, you will get 0 in this case. All right, okay, so now we see that 67 liter of nitrogen at 300 degree and 101 kilopascal is actually 1.42 moles of nitrogen, right? 1.42 moles of nitrogen. And if it is so, how many moles of sodium azide is equal, will be needed to produce 1.242 moles of nitrogen gas? So, so we can just use it in this simple calculation. Just put in this figure, the number of nitrogen, and it turns out that it is 0.947 moles of sodium azide will be needed. Now it is easy. So 0.947 moles is how many gram, is equal to how many grams? What we do is we just multiply by the molecular mass. The molecular weight or molecular mass here. So the molecular weight of this. So the molecular weight of sodium azide or NaN3 is 65.02 gram per mole. So gram per mole, right? If it is gram per mole, what will happen is mole and mole will be cancelled out, only gram remains. So the gram will be 61.57 gram, or if we want to, 61.57 gram of sodium azide will be required to produce 67 milliliter of nitrogen gas. So you imagine how much? Only 61 gram. It is not too much. It is even less than 100 gram. Okay. But if the question is asking you to produce this result in 3 significant figures, so you will do it 61.6. Since it is more than 5, so this figure will push up the previous figure, right? It's more than 5, so it will push up. So it will become 61.6. But if it says you to express in 2 significant figures, then this 5 will push up the figure to 62, round up to 62 gram. All right. So this is it. So we know that how we can calculate the amount depending on or using the stoichiometric ratio or stoichiometry, or by balancing the equation. So balancing is very important. Another type of reaction is that double displacement reaction. Just now we have seen single displacement in where one magnesium was taking up HCl, right? Magnesium was taking up HCl, and that was the single displacement reaction. Here we saw that it is magnesium was taking up a chlorine or chloride to it, and hydrogen was left alone. So this is a single displacement reaction. Double displacement means that both of them from the both side will be replaced by each other. So the double displacement exchange of ions. When exchange of ion, of course, this is a oxidation reduction as well, but for both cases, A is replacing D and C is replacing A, or Yeah, C is replacing B actually. So in that way, both of them are replacing both of the chemical, and that is why we call it double displacement reaction. So double displacement reaction can be in two ways. We can divide into two ways. That is a precipitation reaction, acid, and another one is acid-base reaction. Precipitation reaction means when the double displacement occurs, one of the compound or one of the species, either AD or BC, either one or both, will be deposited at the bottom of the reaction vessel. Like we are doing the reaction in a test tube, right? Excuse my drawing. It's a test tube, let's say. We are doing the reaction in a test tube, and then we add AB and CD. Both becomes, or one of them becomes deposited, and it looks like solid at the bottom. So this is called the deposition or precipitation occurs. We call it the precipitation has occurred because of the mixing. And another way is the acid-base reaction. Acid-base reaction. So for the acid-base reaction, right? For the acid-base reaction, what is happening is these two ions, different type of ions. One is positive ion, one is negative ion. They are mixed up together, and then of course they have been replacement, doubly replacement, and then they become neutralized. They are not ions anymore. Right? They produces water. Most of the, most importantly, not ion. Sorry, there can be still ion, but they have produced water. So that is the acid-base reaction. Any acid and base reaction, you will produce water. Okay, the fraction of it. The rest probably in the solution as the ion, or probably they will be precipitated. But the most important thing is, acid and base reaction, there will be water. That is the most important thing. Now, writing the ionic equation. Why we call it ionic equation? From here we can see, right? From here we can see that A, B, and C, D, we did not put any positive or negative thing here. Right? We did not put any positive or negative thing. For hydrogen and hydroxyl, we have put water, ions on top of them, because we can show it in a ionic form as well. We can show this as ionic form. For this precipitation reaction, we also can show is in ionic form, and we will see the example in a bit. So writing the ionic equations. How do we write the ionic equation, or why ionic equation is important? Ionic equation is important in that way that it allow us to see exact where is the problem, or what do we need to see, or what do we need to focus. It allows us to do that, the ionic equation first. Second, it allows, or it makes the reaction looks simple. Not simple, but much more less complicated for the ionic equation, and so that we can understand the equation, how is going on, or what is actually going inside. So molecular equation shows all reactant and product in a chemical reaction, and ionic only those species ions that actually involved in the reaction, but omit the spectator ions. What is a spectator ion? The spectator ion that does not participate in a reaction. They stay in as it is at the reactant phase and in the product phase. All throughout the reaction, they are just staying as they are. They are not participating in the reaction. So that is why they are called spectator ions. So to convert the molecular equation to ionic equation, what do we need to do? First and foremost, you have to balance the equation anyway. first of all, you have to balance the equation. If you do not balance the equation, then your reaction is not good, or you cannot write the ionic equation, or it will not be correct. It will not be correct. Okay, you will miss out. You will miss out many things. And the second, this is the first one. This is the first one. All right. The second is list down all the aqueous species as separate ions. All the aqueous species. What is the aqueous species? That means which is not solid or gas, or yeah, which is not solid and gas. Other than that, whatever dissolved in water or can be dissolved in water, mostly in the reaction, chemical reaction, there will be water involved as a solvent most of the time. So when there is water involved, those species, they will get dissolved in that water and they will stay as an aqueous species in the reaction vessel. So we have to indicate that they are aqueous by putting AQ in subscript. All right. So this is how the aqueous species is, what do you call it, shown in there. And those aqueous species are most of the, mostly they will do the reaction. Third one is we have to write the ionic equation after cancelling out the common ions. The common ion means the spectator ions. They do not take participate in the reaction. They are just staying as they are in the reactant and product side as well. So we don't want them, to complicate our view of the reaction. So we just omit them out from the either side. For example, it shows that the acid-base reaction, right? So it says that write ionic equation for the following: calcium carbonate and ACl, right? Calcium carbonate, you see that it is solid. S means solid, and HCl means in aqueous, and aqueous means it is in aqueous phase. That means HCl is actually dissolved in water, or we put the HCl in water and then we have added it to solid calcium carbonate. So it means that. All right. It means that it is in aqueous solution. So what is happening? The reaction is occurring, and calcium double displacement reaction, of course, so that both will replace both. So calcium is replacing hydrogen and becoming calcium carbonate, chloride, sorry. And then hydrogen is replacing this calcium, becoming water, and carbon dioxide gas is being produced as well. All right. So in this case, how do you think the reaction is balanced? On the left, we have calcium and in the reactant, and this calcium on the right, we have only one calcium as well. So this is balanced. Thanks God, we don't need to do anything. This calcium is balanced already. What about this carbon and oxygen and hydrogen and chlorine? You see how many species are coming into the in front of us to be solved. So there is one hydrogen also in here, but in this case I have two hydrogen. Okay, so that means there is something that we should be careful about. The hydrogen is 2 already on right side. Left it is 1. Chlorine here. Chlorine is 2 as well. Chlorine is 2 as well. So that means chlorine as 2 as well, and what do you call it? Okay, but on this side is 1 as well. Carbon is 1, it is 1 as well. Oxygen is 3 on this side, and oxygen is 2 plus 1, 3. So we don't need to change calcium and carbonate. It is all the same for reactant and product. Only here chlorine and hydrogen we need to change. And on this side is 2. So if we add 2 here, right? If we add 2, it will be, the reaction will be balanced, right? The reaction will be balanced in this way. So now since the reaction is balanced, we can find out which one are the aqueous ions, aqueous species. HCl is an aqueous species, and H and Cl, we understand that there are two different species, hydrogen and chloride. So they will be in aqueous species, so we have to break them in this way. 2 hydrogen ion and 2 chloride ion, since they are in aqueous. So when there are, we should write aqueous, AQ, subscript AQ, to show that they are aqueous ion. Calcium chloride as well. Calcium is also in aqueous, but this side no need, because this side it is in solid form. It is a solid, but this side on the right side, that is product side, calcium becomes hold on here. On the right side, calcium becomes aqueous, so that we have to express them in aqueous or in ionic form. So calcium we will write aqueous, AQ. Now we see that there are 2 chlorine as well, so this 2 chlorine will be written as 2 chloride ion in this way, and here it is, the aqueous is not added, but please, you need to add this thing. It is printing mistake that it is not added or forgotten. Okay, so now why the calcium is 2 plus? Hydrogen is 1, chlorine is 1. So why calcium is 2 plus? Well, calcium is in group 2, right? Calcium is in group 2. So all the group 2 will have 2 valency. And from here we also can see that since chlorine is 1 and calcium is holding 2 chloride ion, that means calcium should have 2, and only because it has 2 chloride, when it comes, each carrying 1 negative charge, so they cancel the charge and they become neutral, calcium and chloride. So in this way we write the ionic equation. So calcium carbonate we don't need to because it's solid, but hydrogen and chloride, it is aqueous solution. Calcium chloride is aqueous. HCl, water is in liquid form. I didn't talk about liquid form and gaseous form, right? So HCl is in liquid form and gas. So now we have to cancel out those ions that are not doing anything on the both side. We see that hydrogen, it is doing something, right? And then because hydrogen is doing something means hydrogen here on the left side, we see hydrogen here, but on right side, we do not see any hydrogen moving around like it. So that means it has been, it is working or it is being involved in the reaction. But on the chlorine or chloride ion, on the either side, we see exactly the same thing. It has not changed anything or it has not doing anything. So we can just cancel these 2 out. All right. So what is happening? In this way, we can see that These chloride are the spectator ion. So these chlorides are the spectator ion, and we can cancel them from the both sides. So the net ionic reaction remains that calcium carbonate, hydrogen is actually used, then calcium and water and carbon dioxide gas is being produced. So this chlorine does not have any effect on this reaction, or it is not taking part in the reaction. So this is how we should be writing the net ionic reaction for acid and base reaction. Let me take one question here. Upati say, why does the value R change? What does it mean? Upati, can you please clear it a bit? Hello, Upati, I didn't get your question
Yes,
actually. Can you
I mean
please?
the PV over nRT, the value of that
Yeah.
R. You said that sometimes it is not 8.31 and it will be, I'm not sure, another value.
Yeah. Well, 8.31 and another one is 0.0821. So it depends on what type of unit you are using. If you are using kilopascal, so it is 8.31. If you're using ATM, atmospheric pressure, then it will be 0.08. So this is okay. I give you, this is the home, I mean your home task. So go and check the value or unit for R. Okay, what is the unit of R? R is the universal gas constant. What is the unit it has? Go and check. When you go and check, you will see that the value of R changes with the unit changes. When the unit changes, the value of the R also changes. All right. So that is why you will be using two different values for chemical uses only. All right. Is that okay, Ubate?
Yes, sir.
All right, thank you. But you unmute yourself and talk so that when I'm discussing that matter, I can clarify you. All right, question number 3, example 3. 1 gram of calcium carbonate, all right, reacts with 250 milliliter of 1 molar HCl according to the following equation. We have seen this equation, of course. Calculate the volume of carbon dioxide gas released at SLC. Now SLC is standard laboratory condition, right? At the very beginning, first lecture, we already have clarified this, that SLC means standard laboratory condition. At SLC, Vm, molar volume is 24.5. 24.5 liter per mole. But for at STP it is 22.4. So there are few things, not everything. I'm not asking you to remember everything, but few things it is better that you remember. I'm not saying that you must, but it is good that you remember. Okay. So the question is saying that 1 gram of calcium carbonate reacts with 250 milliliter of 0.1 molar HCl. All right. So what we need to do here is find out the quantity of our reactant first. Quantity of the reactant first before we go to the product side. Of course, we have to remember or focus on this product, how much, because this is the question is asking that how much of the quantity will, but we have to focus on the input. If you do not have good input, you have a bad input as well. So input is important first. 1 gram of calcium carbonate, right? It is 250 milliliter of 1, is it 0.1 molar? Okay, yeah, 0.1 molar of HCl. Now we can find, In chemical reaction, once again, this is the thing I will be also reiterating every time, that 1 mole of calcium carbonate, 1 mole of calcium carbonate. If you were in the class, I would make everyone to speak or talk with me, or repeat after me, that 1 mole of calcium carbonate is reacting with 2 moles of HCl, right? If even you do not turn on your mic, please repeat with me, that 1 mole of calcium carbonate is reacting with 2 moles of HCl. Now, when we are saying that mole is reacting with mole, where this kg or gram or tons comes, right? We do not care much how much of the kg or gram is that. We need to know how many moles. And how do we know the number of moles? How can we find the number of moles? How can we find the number of moles? How do we find the number of moles of calcium carbonate here? If we divide it by the molar mass of calcium carbonate, right? Molar mass of calcium carbonate, molecular weight of calcium carbonate, then we find the number of moles. What about for this HCl, which in aqueous solution, that is an aqueous solution. So how do you find the number of moles for HCl? All right. N equals C into V. We have seen this. N equals C into V. From that relation, we will find the number of moles of HCl. And this volume is always in liter. It's always in liter. Never use it as milliliter or any other thing. It will be always in liter. So we can find out quite easily the number of moles of HCl or calcium carbonate and HCl. So calcium carbonate molecular mass of it is calcium is 40, right? Carbon is 12, and then there are 48 gram of oxygen. That means 3 oxygen. That means 16 times 3 is 48. So altogether is 100. So if we divide 1 gram of this by 100, that is the molar mass of calcium carbonate, then we get the number of moles of calcium carbonate. And in this case, we get it is 0.01 mole of calcium carbonate. Now, HCl, N equals C into V, right? So N of HCl equal to C, that means the concentration of, this is the C of the concentration, and V is the volume. Volume, once again, I said that volume should be in liter. So we have to convert these milliliter, 250 milliliter in liter. To convert into liter, we have to divide by 1,000 milliliter so that it becomes liter, and then only we find that this is the number of moles, right? Okay, so this is, now we have come to another problem that first of all, at the beginning, we saw that 1 mole of, oh, it's gone. 1 mole of calcium carbonate is reacting with 2 moles of HCl, right, to produce 1 mole of carbon dioxide. 1 mole of calcium carbonate is producing 1 mole of carbon dioxide, but to produce 1 mole of carbon dioxide, it must react with 2 moles of HCl. Now at hand, I have 0.01 mole of carbonate and 0.025 moles of HCl, right? Whether our reaction will go full, that means whether our all 1 gram of calcium carbonate will finish up or it will not finish up. Whether it will be stopped due to lack of other chemical. So that to know this limiting reactant, to know about limiting reactant is very important, right? You can say that, okay, come back, I mean, go back to that cake baking or cookies baking thing, that you have 1 kg of flour and 1 kg of butter. And what do you need to bake a cake? Yeast, yeah, yeast. You need the bacteria yeast, and what else? Whatever. So, yeah, sugar. Thank you very much. Yes, yes, sugar. I forgot the important thing. So you have 1 kg of sugar. So do you think that you can use all this 1 kg of sugar and all on 1 kg of this butter and milk and everything? No, right? It will not, because before, if you put all together 1 kg, 1 kg, 1 kg, you either you will not produce any cake, or if you produce a cake, it will not be any cake, probably something else it will be produced. And in that case, probably that flour will finish up faster, or sugar will finish up faster, or butter will finish up faster, and then the rest will be as it is, because it cannot produce any more cake. So that is what my point was. My point is to know that which of these, whether this all 1 gram of this calcium carbonate will be converted to this carbon dioxide, or it is only 0.5 gram or 0.4 gram, 0.3 gram, 0.8 gram of it we are actually using to produce the carbon dioxide is produced, and the rest is not being produced, right? So to know that, we have to understand which one is the limiting reactant, right? My God, I need to go a bit faster. Yeah, it is only slide 14. So we need to know about the limiting reactant. So limiting reactant is which one is finished up faster between among these 2 or 3 reactants that we are using to produce the product. Which one is finishing up faster is the limiting reactant. How do you know the limiting reactant? We have to first we have to find out the number of moles of the reactant that is being used, and then we divide them by the stoichiometric ratio, or the coefficient. For this case, although it is not given anything in this calcium carbonate, right? There's nothing given here. I put this 1. Since it is not given anything, is nothing there, so we know it is not 0. Yeah, if 0, then that means there is no calcium carbonate, right? So it is not 0, it is 1, and that is why it is not written, it is not shown here. So since it is 1 and it is 2, so this is the stoichiometric coefficient. We divide the number of moles of the respective reactant by this stoichiometric ratio. So 1 is the stoichiometric ratio, 2 is also the stoichiometric ratio. So we will not this 0.1, but this number of moles. So this number of moles we divide by 2, and this number of mole we divide by 1. Now we see that it becomes the ratio becomes 0.1. It is 0.1012 and 01 and 0125. So this one is smaller, is less than this one, right? 0.01 is less than 0.012, or 0.01 is less than 0.010. If it is even 010, it is still less than this. So which one is less, it will be the limiting reactant. And limiting reactant is important to know because the product will follow the limiting reactant. The product does not care how much the other thing is in the reaction, only the limiting reactant, because the product can only be produced looking or according to the limiting reactant, according to the things that will be finished up faster, right? So in this case, calcium carbonate is limiting reactant, so it will finish up faster, and it does not matter how much HCl is in the solution, no more carbon dioxide will be produced. So that is why the limiting reactant is important. So calcium carbonate is limiting reactant, and the carbon dioxide will be produced here according to the limiting reactant. So since 1 mole of calcium carbonate will produce 1 mole of carbon dioxide, 0.01 mole, which is in 1 gram, right? 1 gram means if we convert 1 gram to mole, that means 0.01 mole, right? 0.01 mole. So if 1 mole of calcium carbonate produces 1 mole of carbon dioxide, 0.01 mole of calcium carbonate will produce 0.01 mole of carbon dioxide, 0.01 mole of carbon dioxide, and 0.01 mole of carbon dioxide at SLC, that means at standard laboratory condition. How many liter? What will be the volume for this at SLC? So again, N equals C into V. You can use, or in a faster way is V over Vm. Since we know that Vm is 24.5 liter per mole. So if we just divide this one, the number of moles multiplies, we'll get the volume of this from this equation. All right. So this is how the limiting reactant is important, or why should we be using the limiting reactant? Okay. So
Sir, your voice is laggy.
hello.
Hi, it is still laggy a bit.
Oh, can you hear me now?
Yes, now it's better.
Okay. What can I do? This network. Okay. So now let's go back. Okay. So this is Vm and different type of molar volume and different type of condition. Question example 4. After this example 4, I will go to that. What is that? Oh, there's an example, and I hope that we can finish it today. After this example 4, I will go to some Menti question for that. Write ionic equation for the following. Ionic equation for the following: that sodium sulfate and barium chloride is producing barium sulfate and sodium chloride. All right. So sodium sulfate and barium. Now, if we look on the either side, balance the molecular equation, we see that here are 2 sodium, but this side is 1. here is 2 chlorine or chloride, sorry, here is 1, right? This side we see the barium is 1, this side barium is 1, thanks God, and sulfate is 1, SO4 altogether 1, and also sulfate is 1. So we do not need to bother about the barium and sulfate because on both sides it's same. Only we have to add another 2 here so that the reaction will be, I mean, the equation will be balanced. So on either side, on the both side, we have 2 sodium, 2 sodium, 2 chloride, 2 chloride, and 1 barium and sulfate each. So this is how we will do the reaction. I mean, balancing the reaction. List which one is the aqueous solution. So we see that this is aqueous, but this is solid and this is aqueous as well. So sodium and sulfate. How do we, from looking at these species, we see that there's 2 sodium and it attached to 1 sulfate. SO4 altogether is 1 sulfate, not SO4, right? SO4 altogether we are considering is 1 sulfate. So there are 2 sodium is attached to 1 sulfate, and there are 1 barium is attached to 2 chloride. So from there we understand that since sodium is 1, we know, and chloride is also 1, we know, sorry, chloride is negative 1, sodium is positive 1. So since 2 positive 1 is attached to 1 sulfate, that means sulfate should have 2 negative charge, right? And sodium is 1 positive charge. Barium as well, it is bonded with 2 chloride. So in this way, I cannot write and show all of them because it takes time. So I'm showing this one. So barium is attached to 2 chloride as well. Cl, yeah, Cl. So that means chlorine is 1 negative. This one is also 1 carrying 1 negative. So to become neutral, it must have 2 positive so that it will become neutral, and then this is neutral. We see that it all over altogether it is not carrying any charge, so it is neutral. So barium chloride. So barium will be 2 positive in that way, and chloride. Now we see all those things, and barium sulfate is solid. So we look for the common ion. Sodium on this side and also on that's this side. Both are not doing anything. They are not doing. Chlorine also, they are not doing anything. They are just staying as it is. So an aqueous medium. So we can just cancel this sodium and chloride ion out, and then that what will be left to it is sulfate and barium, and then barium sulfate is there. So this is the net ionic equation. General rule of solubility, it is something that some students find it very interesting to remember, memorize, but this is not the complete list. This is just an introduction. That compounds containing the following are generally soluble in water: sodium, potassium, ammonia, nitrate, acetate. If these type of ions are in the compound, like one compound is made up of sodium something, sodium phosphate, sodium carbonate, sodium what do you call it, chloride, sodium fluoride, all those things are usually no, carbonate is not soluble, but sodium, yeah, those are soluble. All right, so but when there is exception, of course, there is some exception as well. With the low solubility, group 1 are low solubility, except there are sodium, potassium, and ammonium is there. So this is how we can predict whether one compound will be soluble in the water or not. And when there is a chloride, bromide, iodide, all those things are in the compound unless they are attached to silver and lead. Okay, silver and lead, if it is silver iodide, silver chloride, then it will not be soluble. Other than that, it is soluble. All right. Okay, so now we are moving to the gravimetric analysis, but before that, as I said, I want to, oh, okay, hold on you. I think I can show you the Menti question as well. Oh, go to menti.com, please. Everyone, please go to menti.com. Menti.com. All right. And then use the code P, and I'm putting it here. Use this code. Where's the chat box? Look at your chat box. I put this code. Okay. 34816184. Where does it go? Am I showing you the yep. Okay, so you have only 3 minutes to do it because we don't have much time. I have quite much to. Please vote. Please vote, everyone. I will not see your name, who vote for what, but I just want to see, I just want you to try. So I want everybody to vote. A, B, or C, which one? And I will, after 1 minute, I will start to the timer. Okay. Okay, do it in 2 minutes. Let me make my tea so that I don't feel. Open voting, and then so far how many voter has been there? No, not voting. Why voting closed? Can you vote it? Can you vote? Why? Oh, now it is open. Yes, now it is open. Please vote, vote, vote faster, faster. 2 minutes. 2 minutes. I see one guy vote. I don't know who. Thank you. You have only 1 minute to vote. Mr. How many of us are here? Another 2 faster vote. Those who has not voted yet. Voting closed already. Okay, so let me see what is the total. How do I go there? What do we vote for? What is the result? Yeah, hold on. I forgot what is the result. Where is the result? Should be result here, right? Oh, I've forgotten how to find. I mean, get the result. Did they change the content or I forgot? You're supposed to. Yes, the correct answer is B, but I just want to see who voted. I mean, how much vote we got for what option. Okay, maybe later I will check.
So I think it's in the tab, right? It's in your second tab, right?
Yeah, B. Yes, B is the maximum. 8. One student for C, but here it's supposed to show me here. You're supposed to show me here the result, the bar, but I cannot see it now. Anyway, okay, so thank you very much for your participation. Yes, those who answer for C, now let you know that it is the correct answer is B, because 2 moles of carbon dioxide will produce only because, first of all, you have to know what is the sulfuric acid, H2SO4. If we know H2SO4, then we know that on either side there is a 2 moles of carbon dioxide is left behind, and oxygen, carbon, oxygen, everything. If we because we will add 2 here on sodium in front of sodium hydrogen carbonate. We need to add 2. That means 2 sodium is there. So sodium carbonate, CO2 will be there produced. Okay. So. All right, stop presenting here and then go back to the site. So do you see the slide again?
No, sir.
What can I do? No. Oh, yeah. Yes, I think you can see now, hopefully. Yep.
Yes.
So for another, we have 15 minutes. All right. So, okay. So now we have seen the reaction, how to balance it, this stoichiometry, and what is the purpose of stoichiometry, and the gravimetric analysis that we are moving into. Gravimetric analysis is to find out the composition, the weight percentage, or based on the mass or weight, how much compounds or chemicals inside the sample we have to find out. But as I said that if we do not know what's the limiting reactant, and okay, another term that there is, for the limiting reactant, which is, there are two, among these two, one is limiting reactant that will finish up faster, and the other one is the excess reactant in excess amount. So if one is limiting reactant, there should be another one should be excess reactant. All right. Okay. So limiting reactant, how do you find the limiting reactant, and then what does the limiting reactant is important for? We have to understand. So now we are moving to the gravimetric analysis. And this gravimetric analysis, it involves in weighing. We have to first measure the sample. We have to precipitate it. We have to get some type of solid things out of this liquid, because liquid, if we measure it, there are some consider precipitate. We have to precipitate out what we intended to analysis for, and then we have to filter and then weigh it again. So all these steps are involved in the gravimetric analysis, and most of the things we will be doing in the lab. So the precipitates that forms are silver chloride and silver bromide, silver iodide, all these compounds with silver, and then with iron, phosphorus, magnesium, all these things. The precipitate in gravimetric analysis, first of all, if it is a chloride, if there is a chlorine or chloride inside the sample, we cannot find the chloride, because if it is in chloride form, it will be in liquid form here, right? It will be in liquid form here, and then this chloride in ionic form, it is mixed all around. So we cannot possibly find out the mass of chloride there. So what we can do is, if we get this chloride into a kind of solid matter, and precipitate it out from the solution, by measuring the solution, we can find out the precipitate, right? So this is the gravimetric analysis. So now, for example, it is given that in potato chips, in what type? It's not only Lay's, it can be any other brand. Let's say that 5.4 gram of potato chips is crushed and mixed in a water. I think I will remove this Lay's, otherwise it might be a copyright problem. So it's not lace anymore. People cannot say it's lace. Okay. All right. So 5.4 gram of potato chips from any brand. Let's say we do not know what brand. Crushed and mixed in water to dissolve the sodium chloride to analyze the salt content. Right. We want to know how much salt is in the potato chips, because potato chips is quite salty, and we want chips and salt is there. Excess silver nitrate solution is added. Silver nitrate. Why do we have to add silver nitrate? Silver nitrate is AgNO3. AgNO3 is silver nitrate. So when it is added, if there is chloride, what will happen? It will produce the silver chloride, right? It will produce the silver chloride, and this silver chloride will precipitate down at the bottom, so that then it is a solid, so we can take out the solid, dry it, filter and dry, and then weigh it. So that is why silver nitrate is added. So the silver nitrate silver is added, the precipitate is filtered, dried, and the mass is weighted, and we got the silver chloride. The precipitation is 0.122 gram. 0.122 gram. Calculate the percentage by mass of sodium chloride in the chips. How much sodium chloride is actually in the chips? We have to find out. All right. How do we do that? 5.4 gram of sample. All right. And then we added some sodium and silver nitrate, and we got 0.122 gram of silver chloride. So first of all, first and foremost, once again, now you will understand why I say that even for cooking, you need, if you consider the stoichiometry and the chemistry, it will be better. So sodium chloride and silver nitrate, they are mixing up, or they are reacting, and silver chloride is being formed. Sodium nitrate is also formed, but we are not, it is not our concern, so we will not consider about sodium nitrate. So sodium chloride and silver nitrate are added. So if we convert the ionic equation, chlorine and silver, it produces silver chloride produced 1.122 gram of silver chloride is being produced. All right. How much of sodium is in sodium chloride solution? If 100 gram of potato chips, then how many percentage of it? So first of all, what do? We do not have much clue, right? We have only one simple but solid clue that it is 0.122 gram sodium chloride, silver chloride. 0.122 gram of silver chloride. Look at sodium chloride and silver chloride. Do you see any similarity between them? Can anybody tell me faster? 30 seconds.
They are all 1 mole.
Exactly. Thank you so much. They are all 1 mole. So 1 mole of sodium chloride will produce 1 mole of silver chloride. Right? 1 mole will produce. And again, if we break it down, 1 mole of sodium is attached to 1 mole of chloride, and 1 mole of silver is also attached to 1 mole of chloride, because it's 1:1. It's 1 here, 1 there. It's 1 here, 1 there. So it is very simple. Life is not always this simple, right? So the exam question is not always this simple, but if we do not understand this simple, we cannot do the complex thing. So this is 1:1 reaction, and also these two both are 1:1 reaction mole. 1 mole of sodium chloride will produce 1 mole of silver chloride as well. So let's go move to that and then see 0.122 gram is actually how many moles of silver chloride divided by molecular mass, and then we see that it is actually 8.53 and times 10 power negative mole of silver chloride. All right. Okay, so now we need to know that how many moles. Ratio is 1:1. So exact same number mole of sodium chloride will be in the solution. So this exact same mole of sodium chloride of silver chloride is in the sodium chloride solution. Then we have that multiplied by this molar mass, we get the number of moles, gram, the mass of sodium chloride here. All right. So we see that this is sodium chloride in the solution 0.0402, 0498 percent by mass. If this one is the number of mass of sodium chloride and the sample mass was 5.4 gram of chips, remember we started 5.4 gram chips, so altogether is 0.932, 0.9. So it's almost 1% of salt. It is not less, yeah. So those who are taking this type of junks, please, remember these things, the figures. Percentage of yield. Percentage of yield is how many percent of the product. Yield is product as well. How many percent of the product is being produced is also known as percentage by yield. And sadly, I think we cannot finish, but I will finish after this problems example. So percentage of yield, it says that lead nitrate is producing, reacting with potassium iodide, and potassium iodide is lead iodide is produced. Okay, 37.5 gram of lead iodide is produced from 30 gram of potassium iodide. Okay, so from here to here, we see that 37 gram of lead iodide is produced from 30 gram of potassium iodide. So what is the percentage of yield? All right, what is the percentage of yield is there? Now we see the actual mass of the product by theoretical mass of the product. So it says that, from here we see that 30 gram of potassium iodide we have added. So how many percent, how many gram of potassium iodide, lead iodide will be produced? Now we see that it is 2:1 reaction, right? 2 moles of potassium iodide is 1 mole of lead iodide is being produced. From two moles, 1 mole is produced, right? So 1:2. From here we see it's 1:2, right? So put the values all together, number of moles, convert this potassium iodide in gram, because this is mole ratio. This is not gram ratio. This is a mole ratio. Mole ratio. Once again, we will be always talking about the mole, not gram. So mole, since it's the mole ratio, we have to convert this 30 gram to moles, and then that moles means how many number of moles of lead iodide. So from there we see, of course, from 2 moles it is 1 mole, so half of the moles will be produced. We see that it is 0.0903 moles of lead iodide is being produced. 0.0903 moles of lead iodide means how many grams? We just multiply by the molecular mass. We find the molar mass of this. So since it is 41.6 grams of lead iodide is being produced or found, how much we started with? We started with 37.5 gram of the actual mass of the product, right? Actual mass of the product is says at the beginning is 37.5 gram, but actually the theoretical mass, it was supposed to be produced 41.6 gram. Why it did not produce? We do not know. Maybe there was some other problem. Maybe there was some other, the limiting reactant it was, so it did not finish the reaction or whatever. So it was supposed to be 41.6 gram was supposed to be produced, but we only managed to produce 37.5 grams. So it is 90% yield. The reaction is 90% yield. And in practice, it is never 100% yield. You will never get 100% yield. Okay, so example 7, I will see in the next before we, during the tutorial, before we move to the tutorial, I will talk about it and then we'll move to the tutorial next time. And once again, those who joined just now, we will not have our lab session this week. It will be postponed till next week. Okay, so do you have any question in 1 minute maybe?
No, sir.
Okay, thank you. I'll see you on Friday then, 2 p.m.
Thank you for your time, sir.
All the best.
Okay.
Thank you for joining the class. All the best.
Okay.
Okay, all the best. Bye-bye. Thank you.